1.2 million active clients. To put that into perspective, 1 in 3 people bank with Capitec. With all those people, we actually produce a lot of data. So we pride ourselves in being a data company. To back this, we process 60 billion records daily. We have 100,000 batch processing job runs a month. We have 8 daily feature deployments and 7 million ETL-related queries. We've recently moved over to AWS, which means we get to use fun tools like Redshift for our data warehouse and SageMaker for our model development and our model deployments. Capitec's also driving a lot of open source initiatives. So today I want to take you through our journey in developing this decisioning framework. And I want to start with the requirements, or like our specific requirements. I then want to review the landscape on existing tools and issues or pitfalls we found with them. And then I want to introduce an open source framework called Hamilton from Dagworks, which we use as the foundation for our decisioning framework. I then want to introduce our framework and motivate why we found it necessary to create one in the first place. And then finally, I want to tie it all together with a practical demo and potentially demonstrate how it might be used to solve your issues. So when a lot of people think of machine learning or data science, they think of machine learning and model development. But like businesses typically don't care what accuracies you get with your models. They care if your model can give real business impact or solve real business problems. And when you're trying to solve these problems in like repeatable ways, the problem becomes a lot more complex. You have to worry about how you're going to get that model deployed, how you're going to serve it and orchestrate it with everything else. You also typically want to pre-process features and get them ready for that model. So you're worried a little bit on how you're going to orchestrate that feature development and how you're going to orchestrate this model typically with many other models to get your final results. And then once you've got the results, your model gives a score, like a risk score. So if you're dealing with finance or fraud prevention, you might get a score on how likely a transaction is for being fraudulent. So you still need to tie this in at the end of the day with some business logic to say, do you accept that transaction? Do you block it? Do you try and notify people? And then with those, you typically want to bring in some domain knowledge or domain expertise. So you want to add extra rules and extra features along with that score to determine or try and improve the performance of the model. And then finally, a lot of these sometimes produce these large complex systems, and you want to be able to understand every step of the way internally. So we found that Capitec had like a very unique set of requirements because we had a lot of external solutions that formed our whole ecosystem. And it was very important to us that they were all able to interoperate to form these solutions. So when we turned to like external solutions to try and help out with some of those, we found that there were some issues with interoperability and combining all the tools that we needed to form a solution. We also found that a lot of them, especially when dealing with rule creation, had their own like domain-specific languages or their own UIs that they dealt with. So we found that we'd have to upskill a lot of our data scientists to use them or move over our processes to go into those ecosystems. And then once you've moved over, it's very hard to like move to another one if the need arises. Next, we found that they were offered as a platform rather than a component that we could bring into our system. And when we were dealing with a low latency requirements and high volumes of data, it becomes tricky to orchestrate that to external platforms. And then finally, a lot of them didn't have a data focus. So it was very hard for us to rerun experiments and try out new models with old data and see if it actually worked out. So with this in mind, we set out to develop a checklist on what we called our winning recipe, like what our golden state would look like if we had one. The first item to this was we needed to be able to support both batch and real-time with the same code base. So if you're taking something like credit granting as an example, we often need to score our clients and give them credit scores on like a monthly cadence. But when a client walks into a bank, we also need to be able to give them a score on the most up-to-date information so that we can give them grants. And it becomes very tricky to maintain these two separate code bases for the both batch and the real-time worlds. We also oftentimes share a lot of like components between different departments. So again, going back to credit granting, there might be retail credit and business credit, and there's a lot of overlap in the components that are between these two processes, like shared policies of exclusions on who maybe potentially can't get credit. We also wanted to ensure that it was very easy for our data scientists to get these models from the initial stages of development out into production. So we want to try and iterate fast, and we need to make sure that this integrates well with the existing ecosystems. Next is, as mentioned before, like some of these solutions can form these like large intricate components with many different moving parts. For credit granting, there's the feature pre-processing, there's the credit scoring, there's policies, there's pricing. And at the end of the day, it ends up with being about 250 nodes that you need to orchestrate end-to-end to give a credit grant. So we need to be able to ensure that we are able to dig into each of these components and understand how they contribute to the system as a whole. Finally, it's very important for us, again, to iterate fast. So we want to be able to swap our components and see the overall effects on the entire system end-to-end. So for that, we need to have like a modular design. And for that also often implies we need a stateless execution. Because if we want to run experiments, we don't want to have to run it multiple times and potentially have different results. We want to be able to execute it and see that the results have changed. So using this winning recipe as a guideline, we evaluated lots of open source frameworks, and we decided upon Hamilton as it solved a lot of these issues for us. So Hamilton is an open source Python framework from Dagworks, and basically what it does is it allows you to orchestrate the execution of your Python functions in a module. If you compare it to something like Airflow, Airflow is more a system level orchestrator rather than a function level orchestrator. So we chose Hamilton because it solves the problems of discoverability and documentation. It's able to extract doc strings, output types, input types, and create these visualizations of the DAGs, and so that you can see how all the components are integrated. It also allows you to isolate subsections of these DAGs that you want to execute, and it allows you to execute them in a modular way. Finally, it also has a UI that you can log these executions to, which aids in auditability of the executions. And then finally, it's a Python-based framework, so it integrates very well with our machine learning and our data sciences workflows. So to demonstrate how Hamilton works, I set up these functions that calculate the next values based on previous values. And along the way, it needs to calculate the sum of values and product of values. And it's possible to orchestrate this manually by executing functions in order using a different like main function or something. But with Hamilton, you're able to wrap this module as a DAG or a computation flow. And it's able to work out the dependencies of each of these functions and visualize it for you. And then from there, you can execute it by giving the values as inputs and saying which values you want as the outputs. And then it will execute them in order. But the real power of Hamilton comes in with the fact that you can actually override internal values of this execution graph. So if you wanted to see what would happen if you overrided the value of the product of values, you can do so. And you can also only ask it to return the values you're interested in. So in this case, it will only execute the necessary functions to get to the final result. And then when you execute it, you can also opt to execute it and log it to the UI, and then it will allow you to see the actual code that was executed for each of the nodes. So to recap on the winning recipe so far, Hamilton was able to allow us to get the discoverability and self-documentation of all of these functions, but it also allowed us to do the explainability and auditability, and most importantly, the modular and stateless execution with the DAGs that it created. However, there was no way to get it into an environment where we were able to invoke it directly with batch data or real-time data. And we also felt that there was still a little bit of a barrier to entry with our data scientists. So that's why we decided we needed to create our own framework on top of Hamilton to provide a common set of components that they could use for some of the common tasks that they need. And in turn, it should lower the barrier to entry and make it a lot easier to use. We also extracted a lot of the components as configs so that it was easier to maintain. And then we integrated it into our current deployment architecture so that it was easy to serve. So to demonstrate some of the components I made, I'm going to go back again to a credit granting flow. And in this case, with credit granting, we typically have a few policies that we need to use to run to exclude certain populations from getting a credit based on a few rules. And then from there, we typically segment the population using various features. And then we have scorecards that actually finally calculate the credit score. And then we use a pricing table to determine stuff like the interest rate we're willing to give a client. So this is how we decided to implement our decision trees, which again are used to for policies or potentially in fraud cases to decide whether or not to block or allow a transaction. And what we've done here is we decided to go with a decorator approach because then you can have arbitrarily complex conditions inside each of your nodes to evaluate rather than coming up with some domain-specific language. And then we use strings for the outputs if we want to tie it back to a result that was previously calculated in Hamilton, or you can set a static value, which is what you typically do if you want to give a class to the output of that node. And then, yeah, we can produce the visualization of the tree as well. So then going to scorecards as well. The idea with this is, again, to give potentially credit scores to clients. And we do this by scoring each variable individually by bucketing them. So in the first case, we have a variable 1, which is a numeric variable, and we bucket it in the range potentially between 0, 1, or 1 to 2. And if the value fits in the range of 0 to 1, it will get a score of 10. And then for the second variable, it's more categorical, so it can be text or exact matches, or potentially regex matches, and if it matches each of those, we can give it a score. And then at the end of the day, the score is calculated by summing up all of these bins of values. And then over to pricing tables, which are again used for the interest rates or pricing on the actual values. This is basically just a lookup table where we're trying to determine which category each of the input variables belong to. So in this case, 2 input variables again, and if it belongs between 0, 1, and also 0 to 1 for the first one, then it will get a score of 1. So a lot of the tools that we've used go traditionally where they have a user interface where you design these rules, and then below that, that's driven by configuration, which then gets executed by code. But because we wanted to integrate this into our data scientist workflow, we kind of flip this around, where we have code as a main way of orchestrating these systems end to end. And then we have configuration for each of the components that you can create in these flows. And then finally, we have very specific UIs that are built on top of that. So that gives us a few advantages because we need less upskilling to get our data scientists to use the platform. We have faster time to production because the code can be deployed directly as is when they're developing it. And then we get to exploit the Python ecosystem, which has like rich ecosystem of tools for various purposes. So just an overview of our architecture. Over here, we decided to go with the same patterns as the sklearn containers in SageMaker models. And that sklearn provides a inference.py that you can override various functions to determine how the data is pre-processed from the raw request and how the model is loaded or how the model is executed, and then how the response from the model gets post-processed before it gets returned in a response. So once you develop those, and potentially also we have a config manager class that you can override to load your config from various sources, you can package that with your decisioning logic in code, and then containerize it alongside in a specific directory which gets served. We use Starlet as our serving layer to actually create the API. Starlet's basically just what Fast API is built on top of, but we didn't see it necessary to use Fast API in this case. And then once you have it ready to be as an endpoint, you can actually deploy it in SageMaker, and that will allow you to do real-time requests as an endpoint. But the nice thing about SageMaker is it also allows you to orchestrate these real-time models for batch as well. Internally, it will load the data from S3, micro-batch it, invoke your model, and then store the result back to S3, where we have processes that pick it up and store it to Redshift. And then we integrated with our normal CI/CD pipelines that we use for deploying other models in our environment. Yeah, so now to the fun part, the demo. So I just chose a fraud case. I hope it covers a lot of the topics, but I want to give you an overview of the development process, how easy it is to get this from the initial concept out into production. I also want to demonstrate the power of modularity, and I want to showcase the UI a little bit. Okay, sorry about that. So here's a notebook, which is the environment that our data scientists are normally most comfortable with. Let me just minimize some of these. So typically, the process starts with loading your data and potentially doing some feature development. So over here, I just have a simple data frame of completely made up transactional information. Just a bunch of random things that could maybe be useful for fraud cases. So in this case, the transaction amount, how trustworthy we think a beneficiary is, and a client's daily average spend. You then typically maybe want to work out some additional features on top of this. So potentially maybe how old the beneficiary is from the date they added. So you can have various Python functions calculate these. And in this case, I use this Hamilton magic at the top here to convert the cell into a Hamilton DAG. So as soon as you execute that, you'll get your DAG, which in this case is very linear because it's just calculating various features from some input features. Then on top of that, you might want to start incorporating more complex models. So in normal cases, you might be thinking of doing something like a sklearn or a cat-boost model. With the hype on LLMs, I thought it would just be really funny to see what happened if we gave a transactional JSON structure to our LLM and asked it, do you think this is fraudulent or not? And see what comes out. So in this case, I just have some code to load a transformer pipeline. I wasn't near confident enough to try and ask ChatGPT what it thought. And then I have some functions that just kind of get the data in the correct format for the question. So here's the DAG that gets created. So I format the transactional details, get it into a string, load the transformer pipeline, get the list of transactional messages, and ask the LLM if it's fraudulent or not. So then after that, I have in this case, a decision tree. And the reason we can use a decision tree is it also gives us a nice lever to act really fast. Because what we find, especially with fraud, is as soon as you deploy a model, the accuracies of these models go down because the fraudsters find new ways of committing fraud. So like having decision trees allows our experts to quickly create new rules and try and target very specific use cases. So in this case, I just have a few auxiliary functions up top here. But at the bottom here, I have some of the decision tree logic, which I can combine various features that I've developed previously. And then from there, I can also visualize that tree to make sure it makes sense. The trees get executed from left to right, and you can see each of the components that get executed. And then you can put all these modules in a single DAG, which is the Hamilton's data flow. And then you can execute it with some of the transactional information before. And in this case, it takes a bit because of the LLM, but it brings the sets like the alerts or not alerts from the results of the LLM. So then from here, we want to get it deployed. I have this inference.python file that I spoke about earlier currently in the source directory. And in here, it just shows how we're going to pre-process the data. In this case, I have a bit of custom logic to load the DAG because I want to demo the UI. And then also some custom logic on the prediction. So now going back to this notebook, I basically add this extra write to file command or argument, and I'm able to write each of these cells that I previously tested in this notebook to that source directory. And then they appear up here. And normally at this stage, we might bundle it and deploy it in SageMaker. But over here, just for the demo, I'm going to deploy it locally as a fast API or starlet endpoint. And then I'm going to use ThunderClient to invoke it with the raw transactional data. So this is just the JSON payload as we saw before. And you can have a breakpoint there for some reason. Again, a few seconds because of the LLM, but we get all our alerts or our blocks. And then in this case, if we decide that we didn't like the results of that LLM inevitably, we can actually override here and say LLM is fraudulent and set that to false for each of the transactions. In which case, it will skip the LLM, so this response should be a lot quicker, and we get the results from that. And then if I wanted to dig in a little bit more, I can set which outputs I'm looking into, and in this case, it will return only those nodes rather than the alert or allow that we saw before. And then to further demonstrate this, here's the Hamilton UI, and from today's execution, you'll see that there are 3 new runs. Well, there should have been 3 new runs. Demo day always doesn't go well. Okay, but I'll just go into these ones because they're the exact same execution. So in this case, it executed all the nodes that you get. You get information on the timing, so over years where it was executing the LLMs, and you can dig into some of the actual internal variables and distributions here. Or you can dig into the source code that was executed for that particular stage. And then you can also see, for instance, the other runs that were executed were a bit faster because they didn't have to calculate the LLM's outputs. Oh yeah, here's the new ones 2 minutes ago. Okay, yeah, so that's it for the demo. Okay, yeah. So over here is a QR code for the Hamilton framework if you want to check them out. And then we've open sourced this project. So if you want to check out the open source link, you can go there. We also have a lot of other open source projects that Capitex provided, so you can check those out as well. And then if anyone's interested in like chatting to us, finding out a bit more what we do, there's some Capitec people here and at the back there. Put up your hands if you want to chat to them. But yeah, yeah. Thanks very much. Any questions?
This microphone is going to give me grief again.
John.
The problem that I'm going to have is that, okay, there we go. Press the button. That'll always help. Thank you, Sholto. Do we have any questions from the floor? Or any of the people? Let's check if there's anything online quickly.
Okay. Excellent talk. Love that. Big fan of the number of desktops you have. Did enjoy that too.
Yeah, sure. Close a few.
No, what are you talking about? I mean, a bit of a simple one, maybe not entirely in your team's purview, but what's stopping someone else from just in the JSON payload saying, I want to guesstimate what the LLM Boolean flag is and just set all of it to false? Because like you've exposed that here and to everyone watching this presentation. So
So, I mean, you mean for a real life?
yeah.
Yeah. So, I mean, that would be invoked by something externally. But, I mean, this was just a Playtoy module. So, I mean, it's not anything close to what we'd put into production.
Right.
Yeah, I should have made that very clear. But, yeah. Yeah. Yeah.
Okay, any other questions? All right, two.
Hi, do you do any consideration for real-time feedback loop training on your decision trees? So let's say you mark something as fraud, the person calls in, says it wasn't fraud, it was just me being a shopaholic. Do you go and update the model immediately, or does that go into a bucket for next month's processing?
So the decisioning engine, we haven't like integrated too much yet with the training processes. We want to have the existing training processes used. So like at Capitec, we have ways that we store that data back. We don't have automatically retraining because we feel that you actually need to audit these models and make sure that they have the results that you expect and the accuracies. And sometimes there's also like limitations on how many alerts you can give out. You don't want to be like pestering people with alerts. So yeah, I don't think we'd ever, for this case, like automatically retrain something and send it out. But we do collect that data and have it available for retraining at later stages. Yeah.
Sorry, I missed the first part, so maybe a stupid question, but Hamilton versus Airflow, DBT, any?
Yeah, so I think they solve like different problems. Hamilton's website, they have a in-depth comparison with a bunch of different frameworks, but Airflow is more like a orchestration tool or like more focused on maybe batch jobs or something. But Hamilton is more focused on actually orchestrating these functions, or rather like creating DAGs or data flows that you can execute them one after each other. And with that, I mean, they're just functions that's been executed, so you can actually feed real-time data into it, as opposed to, yeah, just batch.
Thanks. It's kind of crazy to me that you're designing decision trees by hand. Have you benchmarked using like gradient boosting trees or any machine learning method of doing this fraud detection?
Yeah, so I mean, I've been checking out a few. Again, it comes down to the expressiveness, because a lot of those you only have like a single condition that you can have at each step of the way. And for some of our flows, we need like very complex condition, like is it in, or like a set of values, or like does it match a regex condition. So you can't always like do a fair comparison. I think because obviously those are written in C and very optimized, like for some cases those would be faster, but I have done quite a bit of work to optimize this by creating basically a truth table that's just a vector comparison of ands at the end of the day that it compiles down to, which makes it quite efficient. Yeah.
But is it more accurate than a boost table?
Oh, so it doesn't interfere with the development process. So you'd develop the conditions using any other way, or you could integrate like those as a step in this data flow. You don't necessarily have to like use this or that. Yeah.
Any other questions? If not, we can thank our speaker again. And